Yes.
Well, basically, policy, that.
Oh, it's unfortunate. We're gonna go for the dead on exact for that one.
Wherever for you. Right?
Not quite. It's a little bit trickier to get that angle to come out just right. But looks like we can start. Welcome back, everyone. Well, we just got through exam 2, so I guess the first thing we'd want to say is, or we should close that for sure. So we don't get a weird feedback loop. But we got through exam 2, so all I'm waiting for now is the Pocatello Testing Center to send over their exams. I'll try to badger them on Friday if they're a little bit behind and hopefully make that happen. Once all the exam 2s are graded, I'll post the solutions right here on the Moodle website. I'll post the typical statistics down here as well. Well, any other questions, folks, before we get started with today's work? Okay. Well, we're now in section 7.2, the sum and difference identities. We took a look at this document down here. This is the derivation, but we're not as worried about that derivation. It's pretty tough. This is for the curious mostly, so consider that optional reading. At section 7.2, these are what the identities look like after we get through the derivation. The derivation proves this one right here, and then we use a bunch of tricks like cofunction identities, even and odd function identities to get all of the rest of these. Even more tricks give you the values for tangent, alpha plus beta, and alpha minus beta. That's a lot of identities out of nowhere. Some of these are going to be provided on the real exam 3 on the back of the page. I'm going to plan on including these, but we can't fall into a trap because just because they're provided doesn't really help us on actually using them. That's where we have to be very familiar. So sometimes the best strategy is to try to memorize these things. Sorry, say again. And SF? Oh, I gotcha. Yeah, this was the beta Greek, which is, how do you say that in German? Set? Two S's. I wonder if there's a way to typeset that. I'll have to look into it. There probably is. Gotcha.
How do you do that?
Me neither. There's probably a way. Word has a lot of different symbols that you can put in here. So if you ever need to find a symbol, you can go to insert and, well, it's somewhere inside there. I forget exactly how. Probably, yeah. But for these addition formulas, here's how they're, one way you can think about them. You want to try to memorize this block first. Well, these two blocks I did independently. If you could split them up into the sine version and the cosine version, that already helps a lot with memorization. Then notice what happens with the sine version. It always goes sine, cosine, cosine, sine. It'll do it for this version, sine, cosine, cosine, sine. And for every one of these, notice it's been arranged in a very specific way. So that alpha occurs first, beta second, alpha again, and then beta second. You could rearrange terms, absolutely. The author just formatted this way just to help with memorization, to show what the patterns are for this process. The other thing that's an interesting pattern here is sine goes the way you would want. And what I mean by that is plus goes to plus. That's really nice when that happens. Minus goes to minus. Really all you want to memorize for the addition formula for sine is that it goes sine, cosine, cosine, sine. Now, if you go to the other block, cosine is different for the addition formula. It goes cosine, cosine, sine, sine. And same for both versions. But the worst part about it is there is a huge reversal of expectations here to here. The addition formula for cosine gives you a negative between the terms. And if you have the difference formula for cosine, it'll give you addition between the terms. So this one is a little bit more dangerous, but once you've memorized this one, this very first line right here, notice you pretty much have the line right down below because you're only changing one thing, the sign in the middle. So although this is 4 identities, you can really memorize it well with just 2 identities. Memorize the one for sine, and you've got the one for the minus version right here. You're just changing the sign as well. So that's a great way to start thinking about memorizing them. Again, I'm thinking about providing these on the real exam 3, but the more you memorize it, the more familiar you're going to be with these things, and the easier it is going to be to use. So we're going to use it right away and calculate cosine pi over 12. Like was being mentioned, that's an interesting computation because pi over 6 goes over here at 30 degrees, so pi over 12 is over here. And it's actually a pretty hard computation. The result is not pretty either. It's kind of an ugly mess when we get it. So that's the explanation of why we went in distances of 30 degrees all around the unit circle, not 15 degrees pi over 12. That's just a lot of ugly mess to try to memorize. But let's calculate it and see just how it goes. Already there's a mystery here. If you're using the addition formulas for sine and cosine, you're expecting two things, an alpha and a beta. Once you find the right alpha beta, you're just plugging them in and calculating as you go, left to right. But this doesn't provide it. So the very first step on this is we take pi over 12, and we have to rewrite that thing as two different angles. This is the trickiest step. And if this was an exam 3 question, I probably would provide this as an extra hint, just so we're not spending too much time on a 50-minute exam trying to reverse engineer how to break up this angle. But here's how it goes. You want to put two things up in the numerator. I'm thinking of a subtraction because that's going to be the easiest way to get to a single pi. I need two things that are going to add up to pi, and then when we divide by 12, we get a nice division. And usually you can come up with some fast things, like say, how about 3 pi minus 2 pi? That certainly does the job, right? Subtract across the numerator and you get just pi. But now we need to break this into two angles, so we're dividing 12 into both the 3 pi and the negative 2 pi. So we now have 3 pi over 12 minus 2 pi over 12. They still don't look nice, but the reason I picked the 3 pi and the 2 pi is when you divide this one and reduce it, you get pi over 4 minus, this one will turn into a pi over 6. And that's exactly what we want. We now have two angles where we can calculate pi over 4, pi over 6 cleanly using cosines and sines, but we couldn't do anything with pi over 12. That's just never been derived. So we're all set. Our first step is to write out cosine pi over 12 is now equal to cosine of pi over 4 minus pi over 6. You try to fix that formatting. There we go. Well, any questions at all, folks, so far? Okay, to me, this is the hardest step, it turns out. It's just weird math that we almost never do. We always take something like this on the right, simplify it down to pi over 12, but that was just no good to us. We can't calculate on that. So if this is a real exam 3 question, I would provide this as a hint again. For the homework, if you get stuck, don't hesitate to email me. I'll be very happy to discuss the problem on how to break up the angle. But once we get here, notice we have cosine, two angles with a minus. That means we're taking a look at that identity. And here's the strategy that helps a lot with memorization, and it helps a lot with just getting through it in an efficient way. Write out this entire thing, but where alpha and beta are, just put a placeholder, just an ordinary blank. So I'm going to go cosine with a blank, cosine and another blank. This is always tricky. It goes from minus to a plus in the middle. So reversal of expectations, and then sine with a placeholder and sine with another placeholder. Okay, once we have that, we're just following this format, and it's always the same thing. Notice again, it's worth mentioning, in every one of these functions, alpha comes first and beta comes second. That's just to help us put in the right things in the right spot in a clean way. That's how our author decided to format things. So that pi over 4 you see here goes into the first placeholder for cosine and for sine in that way. Does that make sense to that step, just throwing in those values? Awesome. Then we'll just do it again. Pi over 6 goes into the second positions. So it'll go here and here. So we did it, folks. That's using the addition formula right here. All we're going to do next is evaluate all 4 of these trig functions and simplify from there on. But just for the sake of really memorizing how this pattern went down, that's all about the pattern. You could also add this to your notes. We put an alpha here and a beta there. So that was the alpha, that's the beta, and that's alpha, beta again, following this format from above. Well, the next steps are just crank it out. So let's work out this. Oh, we've already got a unit circle, so let's put this here. At pi over 4 for cosine, we're getting root 2 over 2 for our first evaluation. So this equals root 2 over 2 times, and notice we're just completely taking this out and putting in the evaluation. We'll do it again for cosine pi over 6. At pi over 6, that one is a root 3 over 2. There's a plus in the middle, and then just skip over to sine pi over 4. That one matches the cosine value at root 2 over 2. So that will go here. And then sine pi over 6, this one comes out as 1/2. And so here's the results so far. It's not in its most simplified format, but we can simplify it from here on out. On the first fraction, we'll multiply root 2 and root 3 together, and this gives us root 6. The 2 by 3 can multiply together and go inside the root. The denominator becomes 4. And same deal on this one. Across the numerator, it's root 2 times 1, so just a root 2. And across the denominator is 2 by 2 for a 4. Then finally, you could stop at this stage, and that is simplified as it can get, but it looks a little bit nicer if you just add the fractions. It has the least common denominator of 4. So 4 goes down below, and we get root 6 plus root 2. And, I mean, that's not terrible. That's the exact value of cosine pi over 12, but that's not everything anyone wants to memorize, and there would be lots of those kinds of values all around the unit circle that change and vary, just like in this way. Well, we did it, folks. If you ever wanted to know what's cosine at 15 degrees, it's that exactly. Any questions at all with that computation there? Okay, let's see how accurate that is. Let's go back to the drawing board on this thing and take another look at pi over 6. At pi over 6, if we evaluated cosine, we would get this value down here, which is root 3 over 2. But we did a different angle. This one was pi over 12, half as much of a rotation, and I didn't draw this big enough, but we can always zoom in. Zooming is kind of tough, but let's get that to work. If pi over 12 is right here, observe that this means cosine at pi over 12 is a value that's right here. It's bigger than root 3 over 2. Root 3 over 2 is about 0.9, but let's calculate this a little bit better, because if we can get a good estimation there, we'll see if that's even reasonable. I mean, that's kind of a suspicious number in a certain sense. So even though the problem is over, it's a good idea to take a look at this a little bit closer and see if we're going along the right lines. So let me go to just a fast calculator. For upcoming exams, they are now all open calculator. That's exam 3 and the final exam. So it might not be a bad idea to bring just a basic scientific calculator to class. Not that we're doing anything major today, but soon we're going to be calculating cosine, cosine inverse and such on values and getting approximations. So first one let's do is that root 3 over 2, just to get a value to compare. Square root 3 divided by 2 is about 0.866, rounded to the nearest thousand. We typically call that about a 0.9, but we're rounding kind of crudely. The value we just found, which observe, it should be larger, it's closer to 1, is this, root 6 plus root 2 over 4. So let's compare it. Square root 6 plus square root 2 divided by 4. And that's actually remarkably closer to 1, quite a bit more than I would have guessed before calculating this thing. So that tells us, yeah, it looks like we have about the right value. At pi over 12, we're getting something that is definitely a little bit bigger than 8.866. So that means this is a pretty plausible value indeed. Well, any questions, folks, on the computation or the extra look at it? Okay, so that's how the addition formulas go so far. And we have also more formulas for tangent. And these are going to be the major ones. There's obviously going to be formulas for secant, cosecant, cotangent. But you would just take the reciprocal of all of these. If you want one for cosecant, just throw that into the denominator and you have the right thing, because cosecant is 1 over sine. Same for cotangent. If we needed an identity, we would just take the reciprocal of this whole thing, and you have the right thing. But our course, we're really going to focus on just sine, cosine, and tangent for our main computations. That means let's try out this next one. Tangent of 23 pi divided by 12. No clue what that comes out to, but if you need an exact figure, this can make it happen. Well, the addition right here could work out pretty well for us, because if you're starting with 23 pi, you could break it up a little bit easier into two positive quantities. But this is where the problem should start. Let's take 23 pi twelfths and start breaking this thing up. Just like before, I want to partition the 23 pi in such a way that we have two numbers that add up back to 23. But those two numbers we pick, we also wanted to divide into the 12 evenly to give us angles we're just normally used to working with, like the pi over 4, pi over 6. So I'll leave this one up to the class if you spotted anything. What would you put here and here if you're breaking up the 23 pi? I think that's a good choice. Let's go with 12 pi, 11 pi. It looks like on this one, looking at it a little bit closer, we might get stuck on this one. On the next step, we'll have 12 pi over 12 plus 11 pi over 12. And I like this one right here. This one we can work with. This is just going to be pi. And we can calculate tangent at pi, but we're stuck on this one. We still don't know how to calculate tangent at 11 pi over 12. It's just as tough as 23 pi over 12. But that is a good start. This is the name of the game. We're just breaking things up. 9 and 14. Let's try out a 9 and 14. That one sounds like it should work. 9 pi and 14 pi. We'll have a 9 here, 14 here. Let's double check. So for reducing this one, we could divide by 3, and we would have 3 pi over 4. That's good. We can calculate tangent 3 pi over 4. That's just a negative one. Reducing this one, we would divide by 2 to get plus 7 pi over 6. Just as good. We can calculate sine cosines at 7 pi over 6. So same with tangent. So that one works. And this is pretty much the game. It's weird because there are a lot of right answers to this. I was thinking 20 plus 3 pi, 9 pi plus 14 pi does just as well. Now, next thing to do is we take our tangent function down here. We're going to say tangent at 23 pi over 12 is now tangent at 3 pi over 4 plus 7 pi over 6. Now that we have that, we need to write down this identity. But like before, I'm going to write it down using just placeholders, blanks where the alpha is and blank where the beta is. I just scroll down a bit, so let's just hope we can do it by memory. This will be tangent. Good news with tangent is if you see a plus here, it converts to a plus in the numerator. Then tangent of another placeholder. In the denominator, it goes 1 minus. Then tangent. And this is times tangent. You don't need the dot there for multiplication, but I'll just put it in just to emphasize it's multiplying. So that's what it should look like. And we zoom out, we can double check the identity. It should be a tangent plus a tangent. So we got the numerator. 1 minus a tangent times a tangent. So yeah, we've got the denominator as well. I know this is a great way to study the homework. The way you want to work the homework is pretend like you're actually studying for the third exam. You'll have your identities available, but try to write them out from scratch, just for memory. You'll make a few mistakes here and there, but that's normal. That's us learning in the process. The more you do this, writing it out before even checking the formula, the more you're just going to absorb it. You can't help but memorize it the more you write these out. Last thing to do is the same as we did with cosine. Take your 3 pi over 4 and it goes into the first placeholders. So it'll go right here, tangent 3 pi over 4. And as well in the denominator, 3 pi over 4 down here. Next, take the 7 pi over 6, that goes everywhere else, into the second position specifically. And this is where I think I do need a new page. Let's drop this over to the second page, because now we have to calculate all 4 of these tangent functions, but it's not too bad. Let's write out a unit circle here just to aid us. Pi over 4 is in this location, but we're dealing with a 3 pi over 4. They go by odds, so it's right here. 3 pi over 4 is going to give us root 2 over 2 divided by negative root 2 over 2. And so we can just say tangent 3 pi over 4 equals the sine value, root 2 over 2, divided by the cosine value, negative root 2 over 2. That whole thing is just a glorified negative 1. So this negative 1 will go right here and right here. Just temporary highlighting to just visualize where they're going. Next, let's calculate tangent 7 pi over 6, and we'll do the same thing. Any questions so far, folks, with what we've got? Okay, let me change the values here so the diagram doesn't get too busy. We have to say, where is 7 pi over 6? Well, that's pi, which means it's 6 pi over 6. And 7 pi over 6 is just 30 degrees rotated further, so right here. The sine value is right here. It looks like a negative 1/2, and it really is. The cosine value is up here. That's the one that looks closer to 0.9, so it'd be about negative root 3 over 2. In fact, it's exactly that figure. So next, tangent at 7 pi over 6. Yeah, that sounds about right. At 7 pi over 6, we put in the sine value, negative 1/2. Divide by the cosine value, negative root 3 over 2. And this is going to simplify. If you're dividing by 2 in the numerator and denominator, that's just an automatic cancellation. So you can take that shortcut right now. The typical thing we usually do is we write in the numerator, multiply it by the reciprocal of the denominator, cancel this way, and we get, like you said, negative 1 over root 3. You can decide to rationalize that or not. Totally up to you. I wouldn't, because this is not the final answer. This is getting plugged back in here, so it's not the thing I would want to rationalize. We might rationalize the end answer. Yeah, go ahead.
So even though both of the values are negative, we don't cancel out?
Oh, hang out. Yeah, that should have been positive altogether. Thanks for spotting that. So I should have put in, I think that's where I went wrong. I didn't even copy that negative sign when I should have. And that should have been positive altogether. Good eye on that one. Thanks for spotting that. Let me put this in red just to alert anyone who might have miscopied the wrong thing. I neglected to put the sign there. And because of that, I got the wrong side here. It should be positive altogether. Any other questions or weird issues you've spotted at the moment? Okay, now we're back on track with the right value. It turns into a bit of a mess here, in all honesty, but it's not so bad. We're just about there. On the next step, again, we use this highlighting just temporarily. This location becomes a negative 1, so we just drop it in. That whole thing is negative 1 there, plus we move over to this term, 7 pi over 6. That's where we had the 1 over root 3, positive. So plus 1 over root 3 would go right there. Does that make sense to folks on how we're evaluating? Awesome. Then down in the denominator, I'm copying to start 1 minus. Tangent of 3 pi over 4, we'll grab that value, negative 1. So we have double negation going on in this one. That's always extra fun. Then it's going to be multiplied by tangent 7 pi over 6. So we'll plug in that value times 1 over root 3. So there it is. That's the exact value of tangent 23 pi twelfths. It needs some simplifying, and if this was a problem you're doing in the homework, they're going to do a lot of simplifications to this. First thing we should do is definitely correct the double negation and remove the denominator here because this is now a complex fraction. We can definitely simplify that feature. So let me write this in as a new step. We have -1 plus 1 over root 3. Down below, it's 1 plus 1 over root 3. And to simplify this all together, we're just going to wipe out those root 3's here and here, which means all you need to do is multiply by root 3 over root 3. It's going to distribute in, so parentheses here just to visualize it. Which tangent? This one right here? Or
Oh, yeah.
yeah, it turned into the negative, and then we just cancel that double negation at that next step. Other questions at the moment? It's definitely a pretty busy problem for sure. It's one of those problems where it just takes up the whole page as well. That's when that gets exciting, I guess. Well, on our next step, here's what the distribution is going to look like. Here we multiply to get negative root 3. But when we multiply here to here, that's just going to be root 3 divided by root 3. This would turn into a +1 altogether. Then do it again in the denominator. This root 3 multiplies to here, where it's just 1 times root 3. So we put in a root 3. And then finally, this root 3 multiplies here. It's again a root 3 divided by root 3, turning it into a +1. And now we're getting really close to an answer. We have 1 minus root 3 divided by 1 plus root 3. That's kind of curious. To me, that's perfectly and wonderfully simplified. You don't have to do anything further to that. Except if you looked in the back of the book, this is not what you're going to be looking at. They're going to rationalize that denominator. Kind of annoying. That's something we always deal with. I'll leave it up to the class. Should we rationalize it just for the fun of it? Okay. I want to put here that this is a very acceptable answer. Certainly on homework, but this is more for if you're doing an exam question, I would encourage you to just stop right there. There's no need to rationalize things, doing all that extra work on a 50-minute timed exam. You've got the right exact thing. But if you're studying this for the purpose of checking your answer in the back of the book, here's what we're going to do next. Let's take and write it as 1 minus root 3. I think it just looks a little bit better that way. And same with the denominator. 1 plus root 3. Then to rationalize this thing, let me change this and make it a little bit more readable. Let's call this an optional simplification. Once I figure out how to spell simplification, there we go. I think we've got it. So I'll take 1 minus root 3, 1 plus root 3 like we had before. And the idea is we need to multiply by the conjugate of the denominator. That's why I like it in this format. It's easier to see the conjugate. It's just a matter of switching the sign that's in the middle. So now it's a 1 minus root 3 multiplied by 1 minus root 3. These are going to all distribute, but there is a shortcut in the denominator. The denominator is going to be a 1 squared, or just a 1, plus root 3 squared, just a 3, or excuse me, minus a 3. It should just be a -2. We'll work it out and see exactly what we get. First, we FOIL it out in the numerator. 1 distributes through this way, and we get 1 minus root 3 on those multiplications. For the next set, negative root 3 multiplies here, so we get a negative root 3. And then when it multiplies here, that's negative root 3 times negative root 3. It turns into just a +3. Whenever you take something like this, you're really dealing with the root of 9, but that's just back to 3, and that's not a coincidence. Excellent shorthand for this kind of work. So that negative root 3 multiplied by the negative root 3 turns into just a +3. Does that look right to folks on the numerator side? Okay, with numerator done, denominator goes like this. Same exact idea, and there's a bigger simplification. Here to here will be a 1, and here will be a minus root 3. Then distribute again. Here to here is plus root 3. There's always a cancellation in the middle, like you see right here when you multiply by a conjugate. And then here to here, root 3 times root 3 brings a 3 back, but it's negative 3 due to that sign, negative root 3. So that's what our denominator looks like. Down below, these two cancel. Up above, those two are like terms, they'll add together. So we have altogether 1 plus a 3, so a 4 out front, minus 2 copies of root 3, so minus 2 root 3. Down in the denominator, we have 1 minus 3, so a negative 2. Let's move that over just so we can get to the end of the problem here. And then last and final thing that the back of the book would do is divide negative 2 here, so that's a minus 2. The negative 2 will divide up into this one, and it'll turn into a positive root 3 after dividing both things by negative 2. So you can almost see why they did that. This answer is just fine. It's exact, and so is this one, but this one's considered a little bit more simplified because we fully eliminated the denominator on that one. But numerically, they're both exactly the same. And this is what you can do in the back of the book. If you're not sure if you've got the right thing, but you don't necessarily want to rationalize your answer, I encourage you to think in these kinds of terms. So pretend this is your answer right here, and you don't want to change it. If you're fine with it, and I would be too, put it in a calculator. It'll be negative square root 3 plus 1, square root 3 plus 1. So that's the numerical amount we're going for. Then pretend this is in the back of the book. You didn't calculate it, you're just comparing. Go negative 2 plus square root 3. And if you have a match on the decimal expansion, it could still potentially be incorrect. That's the fun part. But you have an extreme amount of numerical evidence. You did the right thing, that is in fact the right answer. So again, rationalization in this class is a nuisance because of the back of the book particularly. You don't have to do it if you're simplified. And this is how you can get out of it, just double checking your answers if you wanted to. Any questions at all, folks, with those two computations so far? Okay, so that's the wild world of addition formulas. My first problem is calculating these kinds of things, which are not easy, but that's a good use of showing why we would care about these things. The next problems, however, are a lot easier. So that's the good news about this section. It says, for example, to use the addition formulas for sine and cosine to now simplify expressions. Evaluations are hard because you have to break up the angles, but if you're simplifying something, these are now way, way easier, and they're a lot easier than we did in section 7.1. The first thing we would do is just look at the format of the function. It goes sine, cosine, cosine, sine, and so that means we're looking at this addition formula. Sine, well, because of the negative, it should be alpha minus beta. So all I'm doing here to start out is I'm just writing down the formula we're about to use. And let me try again. Let me make sure I can fit it. Sine alpha minus beta. If you write down this formula right here, try to do it from memory before checking your notes. And again, that's a good way to really absorb this material. This goes sine, cosine. It maintains the same sign in the middle right here, so we'll definitely have a minus. Then we'll go cosine and sine. Alpha beta for the last, and that's a terrible beta. Let me try again. That'll do. And that's the formula we're about to use. Next, when we come over here, take a look at that format. It went sine, cosine, cosine, sine. It's matching this format as a minus in the middle. We'll put a minus in the middle, and we're going to think of this is alpha, that is alpha, this is the beta, and that's the beta. The whole thing just turned into sine with a minus in the middle. alpha should be the first thing, but alpha in our problem is 3 times phi. Beta in our problem is just phi. And last thing we have to do is, well, combine like terms in the middle. This whole thing was a weird way to look at sine of 2 phi. That's kind of weird in a sense. We use the formula going this way. If we're simplifying, that's a great route to go. And then all we had to do is add the angles together, or subtract them rather, and the whole problem's over. So I'd say these are the fun versions. The ones when you're doing function evaluations, like sine 11 pi over 12, those are the harder ones. But both of them are a great way to use to learn these kinds of formulas. Any questions at all, folks, on running through part A? Okay, let's try it again for part B. It's going to turn into a cosine of something, but probably first thing I would do personally, learning this material, let's just write down the addition formula that goes with it. This one's tricky. Right where the red dot is, the cosine addition formula changes the sign on us. It'll be a plus. So we're dealing with a cosine alpha plus beta the moment you spot the negative between those signs. Then the formula goes like this: cosine, cosine. If there's a plus here, we put a negative, the opposite sign, then sine and sine. And finally, alpha, beta, alpha, beta. So that's the format of what we're about to use. We can come over here and say, that's the alpha in our problem, that's the beta in our problem, and then it duplicates on the next two functions. And so we're pretty much done. Really, most of this problem is just identifying which is the right identity to really use. That's the value in writing these things down, because it's going to help us really spot them when we see them. So the whole thing turns into cosine. There'll be a plus in the middle. Where we see the alpha, that's going to be a pi over 6. And where we see the beta, that would be the pi over 3 altogether. And we're getting there. But one question you might have had is, in this problem, we had no choice. We had to use the addition formula, right? But on this problem, you have choices. You could have calculated cosine, cosine, sine, and sine at those angles, multiplied them together, simplified, and got an answer. The only thing the addition formula did for here is give you a new way to calculate. But actually, this is probably the faster way to calculate. We can add those angles together and get cosine pi over 6 plus, multiply this one by 2 over 2 to get the common denominator. It's now 2 pi over 6. Now in the middle, we can add up the fractions following order of operations to get cosine 3 pi over 6. But let's continue to simplify. 3 pi over 6 is pi over 2. And we know cosine of pi over 2 is 0. So even if you worked all these out, crank them together, you're getting a 0 altogether. But this is the faster way to see it. But maybe not immediately faster. We're learning this identity right here. But once you have that identity down pat, this is far and away the most efficient way to get the value of 0 out. We did it, folks. That's 2 pretty interesting computations so far. Any questions at the moment? Okay, let's try it out again then on part C. This just looks horrific. I'm not even going to lie to you. When I see something like that, it visually does not look pleasing. Close. The only difference is when it comes to tangent, that minus there will turn into a minus inside the function. It's only cosine that has the reversal of the ideas. So the identity we need goes like this: tangent alpha. I'm going with the minus beta only because of that negative sign right there. Goes tangent alpha minus tangent beta divide by 1 minus tangent alpha times tangent beta. But then you're right, it's going to just boil down to using that identity right there, the same one at the very top of the notes. Let's double check. It is a night class right before spring break. It's good to make sure I don't actually copy in a lie. Looks like we got it right. Good. So now that we're at this stage, again, on part C, this could be the worst problem in the world because you can calculate this individually using these kinds of ideas. Then you'd have to calculate this one. It's just as hard, maybe harder. You'd use these values all over again, and you have a huge mess of simplification to do. But like you said, if you use the right addition formula, this just turns into tangent of, that's the alpha, and that's the beta. So it's going to be 11 pi over 21 minus 4 pi over 21. And that looks a lot easier to manage. It's now just one tangent function we're dealing with, not 4 in a fraction. Let's see what we come out with. Yeah, we have a 7 pi over 21. That's good, it divides. This is tangent at pi over 3. You know what, we can get a really fast value on that one. Let's put down a unit circle again, just as extra support. Pi over 3 is 60 degrees. So the sine value is that root 3 over 2. Cosine value is down here, right at 1/2. So numerator, root 3 over 2. Denominator is 1/2. That means the whole thing is square root 3 altogether. So that is like the world's worst way to write the number root 3. But that's the value in simplification. These kinds of things do show up in calculus classes, engineering classes, and we have to know what is it exactly. If you put that whole thing into, say, a calculator, it could have other weird issues. Maybe the machine precision has a problem. But putting root 3 into the calculator, that's easier, and now you have the exact value. Proving this identity right here. Oh, yeah, so we've got some interesting identities down below. Any questions first, folks, on this one before we take a look at some identity work? Okay. Sorry, say again. Yeah, you could potentially lose maybe 1 or 2 points on a 5-point question. This is the major credit, knowing to use the right addition formula and bring it down to that value. But on an exam, if it was a 5-point exam, I would be debating taking off 1 or 2 points. Because evaluation means we have to evaluate the function to get a numerical output altogether. Other questions about that so far?
This might be a dumb question, but so how come you don't do anything with the denominator?
This one right here? Or
out of the whole problem, because it seems like you just work the whole numerator.
exactly. Essentially what I took was really all of this right here, which is identified as all of this, turned into that. So that whole thing is just now that one thing in that one position. The denominator is essentially gone. All the questions so far? Definitely a wild identity. The one for tangent is weird to look at. But the next identity is my favorite one in the whole course. That one right there is a really important identity. It's not a cofunction identity. The cofunction identity for sine, our author writes this way. Personally, I don't like that. The reason I like to write it this way, and it's a real and valid identity, just like this one is because if you look at that carefully, that function has a phase shift of positive pi over 2. And this is the whole reason we call this cosine. It's a cofunction to the sine one. All it is a phase shift. So sine has been phase shift off of cosine in a certain sense. But to prove the identity, well, it's not too bad. You want to start at the worst, most complicated looking side. That's the right-hand side, and just simplify that down. you could potentially differentiate this one actually. Then you'd have to differentiate this side too. It's a complicated derivative. There'd be a chain rule in there. Yeah, different way we could go is that right-hand side we're taking a look at, there's two angles being subtracted. We should just use a difference formula. Let's write out cosine of alpha minus beta. Format for this goes cosine, cosine. This is the dangerous step. Negative goes to plus. I always hate when the expectations get reversed, but there's no getting out of that. By the nature of the universe, it is a plus for this addition formula. And it goes sine, sine, and alpha beta, alpha beta. So that's the identity we're about to use. Next thing we can say is, in our problem, alpha is going to be a theta, and beta is going to be pi over 2. So that gets us started. We now have all the tools ready to go. And here's how it comes together. It'll turn into cosine. Actually, let me just write down what the right-hand side is. Theta minus pi over 2. And now we're getting going. It'll be cosine times cosine. Again, this is the dangerous step. The minus in the middle inside the function converts to a plus outside right here. Then sine and sine. The values we put in are going to be first alpha, or excuse me, that's a theta going right here. And then again, right over here. Next, we'll take pi over 2, plug it into all the remaining positions. But then I have a question for the class. What is cosine at pi over 2? Exactly, this one will come out as a 0. And because cosine pi over 2 is 0, exactly, you could cancel it right at this line if you wanted to. I'll take one more step in the notes just to be specific how it goes. It's turning into cosine of theta times, well, this is just 0 now. So that full first term right here is completely just gone. Next term is sine theta. But it's multiplied by sine pi over 2. That one evaluates to exactly 1. So we get down to that line. And now all we're doing is simplifying. That's gone, so we don't even have to copy it. And 1 times anything is the thing, so that's a sine theta. But sine theta is the left-hand side, and so this verifies, yes, sine is literally just a phase shift to the right by a distance of pi over 2 of cosine. And that's the reason they called it a cofunction to sine itself. And there's a bunch of other cofunction identities. These are not the major, most important things in the world, but our author found it's a good idea to just collect them all in this one spot. Any questions at all, folks, on running through that proof there? Okay, I have one more identity I want to take a look at in the notes, but that one is definitely a good one that we should take a look at after we return from spring break. So this homework assignment for section 7.2 is pushed back pretty far because we should finish it on the 26th of March, meaning the due date is the 2nd of April. It's kind of crazy in a way. If you get started soon on this, then, well, you're working on spring break, and I'd be kind of sorry about that, but it'd be easier if you work on it sooner. If you work on it later, no worries. That'd be my expectation. We're going to start working about this when we come back from the break. But any questions at the moment, folks, with what we've done on these notes? Okay, I think this is a good stopping point for us. I just wanted to mention, over the break, we don't have ordinary office hours and we definitely don't have classes. But if you're working over the break and you need to reach out, go ahead and write that email. Doesn't matter if you're writing it at 9 p.m., 3 a.m., or whatever. I'll be checking my email every day in the morning. That's just my typical routine. So write your questions as soon as you have them. I'll be very happy to help out. But otherwise, I hope you don't have to work too hard this break, and I'll see you folks when we return towards the end of March. Should be a little bit warmer by then. Have a good one, folks.
Thank you.
You betcha. Yes, that would be called a counterexample. That's when the identity itself is just false. And the way you show falseness is you find one value of theta. It has to be in the domain of both functions. But if it breaks equality for one value of theta, you've disproved the whole thing. I would have to throw down something like, say, this. Sine theta equals 2 cosine theta. Something that's like an obvious lie, but it could be true for the right value of theta. But if you pick a specific, like theta equals 0, then the left-hand side is sine of 0, which is 0. The right-hand side is 2 times cosine 0. That's a 2. It's false, so that immediately negates the identity. So the whole identity is false. Now, didn't mean to throw the pin at you.
Great, you don't have to do spring break.
You do the same, try not to work too hard. If you can help it.
Going back to Colorado to clean out a house.
That's tough work. Sorry about that.
So,
Take care of yourself too.
yeah, you do. Take it easy. Good night.
See you later.